This is problem 25 from electromagnetic induction. We have a 100 turn, 10 centimeter square loop. Now, often what I like to do in these problems, if something has a number of turns, I will write that down right away because I have a tendency to forget. If I don't write it down, that I need to multiply things by the number of loops, as you may end up noticing before we get to the end of this section. So if I write it down right away, that helps me to remember to include it. Okay, so it's a 10 centimeter square loop located in a 10 millitesla magnetic field. The magnitude of the magnetic field is increased over a period of 5 seconds. The bulb's resistance is 30 ohms. And I want to find the value the field should be increased to in order to supply the 10 amps necessary to light the bulb. We need two equations here. So we have Faraday's law, which is the main equation that we're using in the electromagnetic induction section. And we also have Ohm's law, which you may have seen in lab already. Usually Ohm's law is written as V is equal to I times R, where V is the voltage and I is the current and R is the resistance. We are going to look at this equation in more detail later on in this course. But for this section, instead of using V for the potential difference, remember that we said the EMF is a special type of potential difference, so that is what we're using for Ohm's law in this section. So I have both my equations here, but before I use them, I need to, on the diagram above, indicate the direction of the induced current in the loop. What is happening to the magnetic field? The magnetic field is being increased. This means that the flux is increasing. If the flux is increasing, I'm going to induce a magnetic field in the opposite direction because Lenz's law says nature abhors a change in flux. So we get a current pointing this way, going in this direction, because the magnetic field is pointed out of the page. And we can actually check that after we use the equations to figure out the value of the current. Okay, so I'm going to use my two equations here. I'm going to need to find the flux, and remember that the flux is equal to the integral of B dotted with dA. But if the magnetic field is uniform, I can just say this is equal to B dotted with A because I can pull the magnetic field outside the integral if it's a uniform field, and then when you integrate dA, you just get A. Okay, now, as we talked about in the previous video, we have to determine what direction we want the area vector to point in. So, you can either have it pointing in the same direction as the magnetic field, or you can have it pointing out of the page. I'm going to say that the area vector is pointing out of the page. So I'm going to say the magnitude of the area vector would just be A, and it's pointing out of the page, so that's in the k-hat direction. But the magnetic field's pointing into the page, so the magnitude is B, but it's pointing in the negative k-hat direction. Therefore, when you do B dotted with A, you have a negative sign here, which makes the flux negative, just based on how I defined the area vector. And remember, if I define a positive direction for the area vector, then when I find my current, it's going to have some sign, and I have to look back at how I define my area vector to determine what the sign for the current means. Okay, so now I have my flux. I can use Faraday's law and say the EMF is equal to the negative derivative of the flux with respect to time. Well, the area of the loop isn't changing, and I could actually use the fact that it's a 10 centimeter square loop to write down what the area is, but I'm not going to do that yet. I'm going to keep it symbolic. So since the area is not changing, oops, I skipped something here. So it's the derivative of the flux with respect to time with the negative sign out front, but the flux itself is negative, so I should have a negative sign in there, which makes the whole thing positive. The area vector could come outside because the area is not changing, so this is just dV dt. It says the magnitude of the magnetic field is increased over a period of 0.50 seconds. We're going to assume that it is increased in a linear fashion. So if you do a graph of the magnetic field versus time, it starts here at 10 milliteslas, and it increases to some value, which we're going to find. And I'm going to assume it's increased linearly so that I can just say dB dt is equal to my slope, which is the change in the magnetic field over the change in time. Okay, so unless they tell you otherwise, you can say that. And if it's not increased linearly, well, the best you can do is find the average value anyways, which would be what you get when it is increased linearly. Okay, so pretend it's linear unless you're told otherwise. And I know what B initial is. I can say this is B final minus B initial divided by delta t, and delta t is equal to 0.5 seconds. Let me write down some of the things that I know. So delta t is equal to 0.5 seconds, and the area would be equal to 10 centimeters squared. The initial value for the magnetic field is 10 milliteslas, and the resistance of the bulb is equal to 30 ohms. And don't forget, I already forgot, because here, when I did the area, it should be N times that. So we'll just say times 100. I mean, or you could say the flux is equal to B times N times A, as long as you get the N in there somewhere. So I have an expression for the EMF. I only have one unknown here, which is B final. That's what I want to find. To what value should the field be increased in order to supply the 10 milliamps necessary to light the bulb? So now I'm going to use Ohm's law to compare the current with the EMF. So I times R must be equal to A times B final minus B initial over delta T. And then I want to solve for B final. So we have divide by A and multiply by delta T, and you have B final minus B initial is equal to I times R times delta T divided by A. And then B final is equal to B initial plus I R delta T times A. This works out very nicely because B final is greater than B initial. But if B final was not greater than B initial, then what you would need in order to make your equation work is a negative value for I, which means I would have to be pointing in the opposite direction. But remember that I said the area vector was pointing out of the page, so out of the page is the positive direction, and we said the current is going this way, which would be the positive direction. So it all works out. And then we can just solve for B final. So you have all the values that you need here, so you can plug them in on your own. But you should get for this, B initial is 10 milliteslas, so that's 0.01 teslas plus for everything here with a current of 10, oh, I didn't write that down here. So the current is 10 milliamps. The resistance is 30 ohms, delta T is 0.5 seconds, and the area vector is 100 times 10 centimeters squared. You should get 0.15 teslas, which gives you, for the final answer, 0.16 teslas. And that concludes problem 25.